Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with trigonometry in the world. A complete study of trigonometry has to leave the chalkboard and look at the world. The same 6 functions you have been learning are at work everywhere, from satellite navigation to medical imaging to musical instruments. This section is a brief tour of how trigonometry shows up in practice. A sample, not a complete survey. Surveying and the Haversine formula. The oldest application of trigonometry is triangulation, using measured angles and one known length to compute inaccessible distances. The Great Trigonometric Survey of India, begun in 1802, used triangulation across a 2,400-kilometer grid of carefully measured triangles to produce the first scientific measurement of Mount Everest's height in 1856. Modern surveying still works on exactly this principle, with the angles read by total station theodolites accurate to a single arcsecond. The Earth, however, is not flat, so the plane laws of sines and cosines are only approximations, good for short distances. For long distances, flights between cities, GPS positioning, ocean navigation, you need spherical trigonometry, where the sides of a triangle are arcs of great circles on a sphere. The most commonly used result is the Haversine formula for the great circle distance between 2 points. Equation 37, the Haversine formula. The great circle distance d equals 2r times the arcsine of the square root of sine squared of delta phi over 2 plus cosine phi 1 times cosine phi 2 times sine squared of delta lambda over 2. Here r is the radius of the sphere, about 6,371 kilometers for the Earth. Phi 1 and phi 2 are the latitudes of the 2 points in radians, and delta phi and delta lambda are the differences in latitude and longitude. The formula is named after the Haversine function. Hav of theta equals sine squared of theta over 2, coined by James Inman in 1835 to make exactly this formula clean. The Haversine formula is what every airline routing algorithm and every GPS distance calculation uses, with small corrections for the Earth's slight oblateness. Figure 35. 2 points on a sphere are connected by an arc along a great circle. The latitudes phi 1 and phi 2 are measured from the equator, and the longitudes lambda 1 and lambda 2 from the prime meridian. The arc between them is the great circle distance, the shortest path on the sphere's surface, computed by equation 37 from the 4 coordinates and the sphere's radius. Worked example, New York to London. New York City is at approximately 40.71 degrees north, 74.01 degrees west, and London is at approximately 51.51 degrees north, 0.13 degrees west. Using r equals 6,371 kilometers for the Earth's mean radius, find the great circle distance between the 2 cities. Convert all 4 coordinates from degrees to radians. Phi 1 equals 0.7104, lambda 1 equals negative 1.2918, phi 2 equals 0.8991, and lambda 2 equals negative 0.00227. Compute the differences in latitude and longitude. Delta phi equals 0.1887, and delta lambda equals 1.2895. Evaluate the expression under the square root in equation 37. Sine squared of 0.1887 over 2 plus cosine of 0.7104 times cosine of 0.8991 times sine squared of 1.2895 over 2 is approximately 0.0089 plus 0.1704, which is about 0.1793. Take the square root and apply the inverse sign. The arcsine of the square root of 0.1793 equals the arcsine of 0.4234, approximately 0.4372 radians. Multiply by 2r to recover the great circle distance. D equals 2 times 6,371 times 0.4372, approximately 5,570 kilometers. The great circle distance is approximately 5,570 kilometers, very close to the actual flight distance of roughly 5,560 kilometers. Astronomy, Parallax, and the Parsec. Trigonometry is how we first measured the distances to the stars. As the Earth orbits the Sun, a nearby star appears to shift slightly against the background of more distant stars, a phenomenon called stellar parallax. The angular size of this shift, measured at 2.6 months apart, gives a tiny triangle, the Earth's orbit on one side, the line to the star on the other, that yields the star's distance by basic right triangle trigonometry. Figure 36. Stellar parallax. The Sun sits at the center, with the Earth shown at two positions on its orbit, half a year apart and separated by 2 astronomical units. A nearby star, far beyond the orbit's radius, appears to shift slightly against the distant background as the Earth moves. Half the apparent shift is the parallax angle p, and the star's distance d satisfies the tangent of p equals 1 astronomical unit over d. Because p is always tiny for real stars, the tangent of p is approximately equal to p in radians. The parsec, the basic unit of stellar distance, is defined as the distance at which 1 astronomical unit subtends a parallax angle of exactly 1 arcsecond. 1 parsec equals approximately 3.26 light-years, or about 3.086 times 10 to the 16th meters. The nearest star, Proxima Centauri, has a parallax of about 0.7687 arcseconds, placing it at 1 divided by 0.7687, approximately 1.30 parsecs, or 4.24 light-years. The same parallax principle, scaled up, lets space telescopes such as Gaia measure distances to billions of stars across the Milky Way. Try it. Parallax distance. A star has a parallax angle of 0.1 arcsecond as seen from Earth. Part A. What is the star's distance in parsecs? Part B. What is its distance in light-years? Part C. If the parallax angle had been 0.01 arcseconds instead, how does the distance change? Pause the video now and give it a try. Oscillation and wave motion. The deepest reason trigonometry appears everywhere in physics is that anything vibrating around a stable equilibrium does so sinusoidally for small displacements. A mass on a spring, a pendulum swinging gently, an atom jiggling in a solid, all obey, to a very good approximation, an equation whose solution is x of t equals a cosine of omega t plus phi. The angular frequency omega depends on the stiffness of the restoring force and the mass of the object. Equation 38, the angular frequency of simple harmonic motion. Omega equals the square root of k over m. Here k is the stiffness of the restoring force, the spring constant, in newtons per meter, and m is the mass in kilograms. The period of the oscillation is t equals 2 pi over omega, and the frequency in cycles per second is f equals 1 over t, which equals omega over 2 pi. Figure 37. A mass hangs from a spring, oscillating up and down, and its position as a function of time traces out a cosine curve. The amplitude a is the maximum displacement from equilibrium, and the period t is the time for one complete cycle. The same curve describes a gently swinging pendulum, a pure musical tone, and the voltage of household alternating current power. A wave traveling along a string or through the air has the form y of x and t equals a sine of kx minus omega t plus phi, where k equals 2 pi over lambda is the spatial frequency and lambda is the wavelength. Light bending as it passes from air into glass obeys Snell's law. Equation 39, Snell's law. N 1 times the sine of theta, 1 equals n2 times the sine of theta, 2. Here, n1 and n2 are the refractive indices of the two media, and theta 1 and theta 2 are the angles of incidence and refraction, each measured from the normal to the surface. Snell's law is why a pencil in a glass of water looks bent, and how an optical fiber traps light inside itself by total internal reflection. Try it, mass on a spring. A mass of 0.5 kilograms hangs from a spring with stiffness 50 newtons per meter. Part A. Find the angular frequency omega using equation 38. Part B. Find the period t. Part C. If the mass is pulled down 5 centimeters from equilibrium and released from rest, write a formula for its position x of t as a function of time. Pause the video now and give it a try. Fourier's theorem: every signal is a sum of sines. The most ambitious idea in this section is also one of the most important in all of modern science. In 1822, the French mathematician Joseph Fourier proved that any reasonable periodic function, not just sines and cosines themselves, but square waves, sawtooth waves, the sound of a violin, the electrical pulse of a heartbeat, can be written as a sum of sines and cosines. The frequencies in that sum are integer multiples of the fundamental frequency, called harmonics. The decomposition is called the Fourier series. Equation 40, the Fourier series. F of t equals a0 over 2, plus the sum from n equals 1 to infinity of an times cosine of n omega t, plus bn times sine of n omega t. The coefficient a0 is the constant term, an and bn are the cosine and sine coefficients of the nth harmonic. Omega is the fundamental angular frequency, and n runs through the positive integers. The coefficients an and bn are integrals you would compute in a calculus course. But the point is the structure. Every periodic signal is secretly a sum of pure sinusoids. Figure 38. A square wave is approximated by a Fourier series, with the target square wave drawn as a thick dashed line. A single sine wave hits the right peaks and troughs, but misses the corners. Adding the third harmonic bends the curve toward the square shape, and adding the fifth brings it closer still. With enough harmonics, the sum becomes indistinguishable from the square wave everywhere except at the sharp corners. Fourier's theorem is at work all around us right now. First, audio compression. The MP3 and ASC formats stores only the loudest Fourier components and discards the rest. Second, image compression. JPEG uses the discrete cosine transform, a close cousin of the Fourier series. Third, wireless communication, in the form of radio modulation, is a shift in the Fourier frequency domain. Fourth, medical imaging, MRI and CT, reconstructs images by inverting a Fourier transform. And finally, most of quantum mechanics is formulated in the Fourier, or frequency, domain. The very device you are using to watch this video book performs, Fourier transforms thousands of times each second. Here is a final reflection. The Fourier theorem says that a sinusoid is, in a precise sense, a fundamental building block. Every periodic phenomenon is built from sinusoids, the way every integer is built from prime numbers. Why should sine and cosine, born from triangles, generalized to circles, have this universal role? What does it suggest about the deep relationship between geometry, algebra, and the physical world? That wraps up trigonometry in the world. That completes the chapter. If you found this helpful, like and subscribe and support the channel.